हेलो स्टूडेंट्स, ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਸਾਡਾ ਅੱਜ ਦਾ ਡਿਸਕਸ਼ਨ ਮੋਲੀਕਿਊਲਰ ਆਰਬਿਟਲ ਥਿਊਰੀ ਬਾਰੇ ਹੈ, ਪਰ ਪਹਿਲਾਂ ਅੱਜ ਦੇ ਟੌਪਿਕ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਬਾਰੇ ਨਜ਼ਰ ਪਾ ਲਈਏ।
Upon completion of this topic, learners will be able to describe linear combination of atomic orbitals, discuss molecular orbital theory and its characteristics, draw molecular orbital diagrams.
In 1932, Hunt and Millikan proposed molecular orbital theory to explain the formation of chemical bond and the behavior of molecules like their relative bond strength, paramagnetic and diamagnetic nature. According to this theory, when two atomic orbitals combine or overlap, they lose their identity and form new orbitals. The new orbitals thus formed are called molecular orbitals. The electrons in the molecular orbitals are under the influence of all the concerned nuclei. Thus, the molecular orbitals are polycentric in nature. On the basis of molecular orbital theory, molecular orbitals are formed by the linear combination of wave functions of atomic orbitals of the constituent atoms of the molecule. Students, let us now discuss about LCAO or linear combination of atomic orbitals. Wave mechanics states that an electron has both wave as well as particle nature. An atomic orbital is an electron wave. Psi represents the amplitude or wave functions of the electron wave of atomic orbital. But I know, students, a question can arise in your mind. How can we obtain value of the wave function? Well done, students. We have studied about Schrödinger wave equation. We can calculate values of wave functions with the help of it. But Schrödinger wave equation can be helpful only for the calculation of wave function in case of only monocentric systems. It is not possible to calculate wave functions for more than one electron, especially in case of molecular orbitals with the help of Schrödinger wave equation. As a result, LCAO, that is linear combination of atomic orbitals, comes into existence. With the help of LCAO theory, it is possible to calculate wave functions for the system containing more than one electron. आओ hydrogen atom da example लेंदे हाँ. The molecular orbitals of hydrogen molecule are formed by the linear combination of the wave functions of the participating atomic orbitals of hydrogen atoms. They may combine either by addition or by subtraction. Let psi A and psi B represent the wave functions of the two combining atomic orbitals A and B of two hydrogen atoms taking part in chemical combination. When the two electron waves are in phase, means they have same sign of wave functions. They add up to give a new wave function. Psi is equal to psi A plus psi B. In other words, the two electron waves of the bonding atoms reinforce each other due to constructive interference. Let us look at the shown image. Addition of two wave functions is shown here. When the two electron waves are out of phase, means they have opposite sign of wave functions, they will combine by subtraction to give new wave function. The resulting wave function is psi star is equal to psi A minus psi B. Let us look at the shown image. Subtraction of two wave functions is shown here. Probable electron density is given by square of amplitude. It can be denoted as shown here with help of psi square. Psi square is equal to psi a square plus psi b square plus 2 psi a psi b. Psi star square is equal to psi a square plus psi b square minus 2 psi a psi b. Molecular orbitals resulting from the addition of the wave functions are known as bonding molecular orbitals, whereas molecular orbitals arising from the subtraction of the wave functions are called as antibonding molecular orbitals.
When two 1s atomic orbitals of hydrogen atoms combine by the addition of their wave functions, ਤਾਂ bonding molecular orbital ਬਣਦੇ ਹਨ। Bonding molecular orbital ਵਿੱਚ ਜ਼ਿਆਦਾਤਰ ਇਲੈਕਟ੍ਰੋਨ ਡੈਂਸਿਟੀ bonded atoms ਦੇ ਨਿਊਕਲੀਆਈ ਦਰਮਿਆਨ ਮੌਜੂਦ ਹੁੰਦੀ ਹੈ। As a result, nuclei are shielded from each other. ਇਸ ਕਰਕੇ ਨਿਊਕਲੀਆਈ ਦਰਮਿਆਨ repulsion ਬਹੁਤ ਹੀ ਘੱਟ ਹੁੰਦੀ ਹੈ। Electrons present in bonding molecular orbital always tend to hold the combining nuclei together and provides stability to a molecule. Thus, bonding molecular orbital has lower energy than the combining atomic orbital. When two 1s atomic orbitals of hydrogen atoms combine by the subtraction of their wave functions, antibonding molecular orbital is formed. But in antibonding molecular orbital, most of the electron density exists away from the space between the nuclei. As a result, nuclei are less shielded. ਇਸ ਕਰਕੇ ਨਿਊਕਲੀਆਈ ਦਰਮਿਆਨ repulsion ਬਹੁਤ ਜ਼ਿਆਦਾ ਹੁੰਦੀ ਹੈ। There exists a place in antibonding molecular orbital ਜਿੱਥੇ ਕਿ electron density 0 ਹੁੰਦੀ ਹੈ। It is known as nodal plane between two nuclei. It is also responsible for high repulsion between the nuclei. Thus, electrons present in antibonding molecular orbital try to destabilize the molecule and energy of antibonding orbital increases. It means antibonding molecular orbital has higher energy than the combining atomic orbitals. ਵਿਦਿਆਰਥੀਓ, energy level diagram ਨੂੰ ਵੇਖੋ ਜੋ ਕਿ ਹਾਈਡਰੋਜਨ ਐਟਮਸ ਦੇ 2 1s atomic orbitals ਨੂੰ ਦਰਸਾ ਰਿਹਾ ਹੈ। Both 1s atomic orbitals are shown to have one electron each having opposite spin. ਇਹ ਦੋਵੇਂ 1s atomic orbitals combine ਕਰਕੇ bonding ਅਤੇ anti-bonding molecular orbitals ਬਣਾਉਂਦੇ ਹਨ। Bonding molecular orbital has less energy than the combining atomic orbital, while antibonding molecular orbital has higher energy than the combining atomic orbital. This lowering of energy of bonding molecular orbital than combining atomic orbitals is called as stabilization energy, while increase in energy of antibonding molecular orbital than combining atomic orbitals is called as destabilization energy. Molecular orbitals of diatomic molecules are represented by sigma, pi, and delta. The sigma molecular orbitals are symmetrical around the bond axis, whereas pi molecular orbitals are not symmetrical. Let us look at the image showing formation of sigma 1s molecular orbital by axial overlap of the atomic orbitals. Here, two atomic orbitals with positive sign of wave functions are shown in red color. Let us look at the image showing formation of sigma star 1s molecular orbitals. Here, two atomic orbitals with opposite sign of wave functions is shown in red and blue color. Let us look at the image showing formation of sigma 2 pz molecular orbitals. In this case, sigma 2 pz is taken along internuclear axis. Here, atomic orbitals with opposite sign of wave functions is shown in red and blue color. Let us look at the image showing formation of sigma star 2 pz molecular orbitals. When two 2px atomic orbitals combine sidewise, two pi bonding and antibonding molecular orbitals are formed. Let us look at pi 2px bonding molecular orbital as well as pi star 2px antibonding molecular orbital.
Students, let us now discuss salient features of molecular orbital theory. The molecular orbital is the region in space comprising the nuclei of combining atoms around which there is maximum probability of finding electron density. In a molecule, the electrons are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. The atomic orbitals of proper symmetry and comparable energies combine to form molecular orbitals. While an electron present in an atomic orbital is influenced by only one nucleus, electrons present in a molecular orbital are influenced by two or more nuclei depending upon the number of atoms in the molecule. Therefore, an atomic orbital is monocentric, while a molecular orbital is polycentric. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. For example, formation of two molecular orbitals can take place when two atomic orbitals combine. One is known as bonding molecular orbital, while the other is known as antibonding molecular orbital. The bonding molecular orbital has lower energy and that's why greater stability than the corresponding antibonding molecular orbital. Just as the electron probability distribution around the nucleus in an atom is denoted by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is denoted by a molecular orbital. The molecular orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule like atomic orbitals. Students, now we will discuss conditions for the combination of atomic orbitals. The combining atomic orbitals must have the same or nearly same energy. One s orbital can combine with one s orbital but not with 2s orbital because the energy of 2s orbital is higher than 1s orbital. The combining atomic orbitals must have the same symmetry about the molecular axis. 2s atomic orbital can combine with 2pz atomic orbitals having same sign of wave function along molecular axis, but 2s atomic orbital cannot overlap with 2px atomic orbital due to improper orientation is also shown. The combining atomic orbitals must overlap to the maximum extent.
Shapes of atomic orbitals. Let us discuss shapes of the various molecular orbitals when atomic orbitals are of s and p type in nature. Students, first we will observe combination of two 1s atomic orbitals along internuclear axis. When both the 1s atomic orbitals are having positive sign of wave functions, their overlap will result in the formation of bonding molecular orbital. Here, combination of two 1s atomic orbitals having opposite sign of wave functions is also shown. As a result, formation of antibonding molecular orbital takes place. This image depicts that two 2pz atomic orbitals combine along internuclear axis, resulting in formation of sigma 2pz bonding molecular orbital and sigma star 2pz antibonding molecular orbital. If the lobes of the two 2pz atomic orbitals which are facing each other have same signs of the wave functions, their axial overlap will result in sigma 2pz bonding molecular orbital. If the lobes of the two 2pz atomic orbitals which are facing to each other have opposite signs of the wave functions, their axial overlap will result in the formation of sigma star 2pz antibonding molecular orbital. The shown image depicts that two 2px atomic orbitals overlap along the sides to form two molecular orbitals. The lobes of the 2px atomic orbitals which are facing each other have same signs, plus plus and minus minus of the wave functions, overlap to form pi 2px bonding molecular orbital. When lobes of the 2px atomic orbitals which are facing each other have the opposite signs, plus, minus and minus plus of the wave functions, overlap sidewise to form pi star 2px antibonding molecular orbital. Similarly, two 2py atomic orbitals overlap along the sides to form 2pi molecular orbitals, both bonding as well as antibonding orbital.
Now we will discuss energy level diagram for Homo Nuclear diatomic molecules before starting our discussion on it. Let us discuss the general characteristics of energy level diagram for molecular orbitals. Those are: the relative energies of the molecular orbitals depend upon the energies of the corresponding atomic orbitals involved in their formation. Within the same pair of molecular orbitals, the bonding molecular orbital will have lower energy than the antibonding molecular orbital. By the combination of two 1s atomic orbitals, formation of two molecular orbitals sigma 1s and sigma star 1s take place. The 2s and 2p atomic orbitals of two bonding atoms form 8 molecular orbitals. 8 bonding and antibonding molecular orbitals are as follows. Bonding molecular orbitals are sigma 2s, sigma 2pz, pi 2px, pi 2py. Antibonding molecular orbitals are sigma star 2s, sigma star 2pz, pi star 2px, pi star 2py. Pi 2px and pi 2py molecular orbitals have equal energies. Pi star 2px and pi star 2py molecular orbitals have equal energies. The energy of sigma 2pz is higher than that of pi 2px and pi 2py orbitals and is lower than corresponding antibonding molecular orbitals, that is pi star 2px and pi star 2py orbitals in case of Homo nuclear diatomic molecules like lithium, beryllium, boron and nitrogen, while in oxygen, fluorine and neon like diatomic molecules. The sigma 2pz bonding molecular orbital has lower energy than pi 2px and pi 2py bonding molecular orbitals. Sigma star 2pz has the maximum energy. The increasing order of energy of different molecular orbitals belonging to Homo nuclear diatomic molecules, lithium, beryllium, boron and nitrogen is: sigma 1s has lower energy than sigma star 1s, it has lower energy than sigma 2s, it has lower energy than sigma star 2s, it has lower energy than pi 2px, its energy is equal to pi 2py. It has lower energy than sigma 2pz, it has lower energy than pi star 2px, its energy is equal to pi star 2py. It has lower energy than sigma star 2pz. For diatomic molecules such as oxygen, fluorine and neon, the increasing order of energy of molecular orbitals is: sigma 1s has lower energy than sigma star 1s, it has lower energy than sigma 2s, it has lower energy than sigma star 2s, it has lower energy than sigma 2pz, it has lower energy than pi 2px, its energy is equal to pi 2py. It has lower energy than pi star 2px, its energy is equal to pi star 2py. It has lower energy than sigma star 2pz. In oxygen, fluorine and neon diatomic molecules, the sigma 2pz bonding molecular orbital has lower energy than pi 2px and pi 2py bonding molecular orbitals. Its reason is the energy difference between 2s and 2p orbitals is quite large. However, from lithium molecule to nitrogen molecule, the energy difference between 2s and 2p orbitals is very small, and molecular orbitals sigma 2s and sigma 2pz are so close that they interact or mutually combine. As a result, the energy of sigma 2s orbitals gets lowered and energy of sigma 2pz orbitals gets raised. Thus, in the molecules from lithium to nitrogen, sigma 2pz molecular orbital is at a higher energy than pi 2px and pi 2py molecular orbitals because of orbitals mixing effect. Students, these molecular orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule like atomic orbitals. Students, from the electronic configuration of the molecule, stability of molecules in terms of bond order and magnetic properties of molecules can be predicted. Bond order is defined as half of the difference between the number of electrons present in bonding as well as antibonding orbitals, where Nb represents the number of electrons in bonding molecular orbital and Na represents the number of electrons in antibonding molecular orbitals. So, bond order can also be written as bond order is equal to 1 upon 2 into number of electrons in bonding molecular orbital minus number of electrons in antibonding molecular orbital. Bond order gives the following valuable information: stability of the molecule or ion. If bond order is positive, it means number of bonding electrons is greater than the number of antibonding electrons. Molecule will be more stable. Bond dissociation energy. Bond order is proportional to bond dissociation energy. Higher will be bond order, higher will be bond dissociation energy. Lower bond order will be responsible for the lower bond dissociation energy. Bond length. Bond order is inversely proportional to bond length. If bond order is higher, bond length will be smaller and vice versa. Magnetic properties. Number of unpaired electrons helps in deciding the paramagnetic character. If there is no unpaired electron in a molecule, it will be dimagnetic in nature. Molecular orbital diagram for the formation of oxygen molecule. ऑक्सीजन मॉलिक्यूल ਦੀ ਫਾਰਮੇਸ਼ਨ ਵੇਖਦੇ ਹਾਂ। ਇੱਕ ਆਕਸੀਜਨ ਮੋਲੀਕਿਊਲ 2 ਆਕਸੀਜਨ ਐਟਮਸ ਦੇ ਕੰਬੀਨੇਸ਼ਨ ਨਾਲ ਬਣਦਾ ਹੈ। ਜਿਵੇਂ ਕਿ ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਆਕਸੀਜਨ ਦਾ ਐਟੋਮਿਕ ਨੰਬਰ 8 ਹੈ ਅਤੇ ਇਸ ਦੀ ਇਲੈਕਟ੍ਰੋਨਿਕ ਕਨਫਿਗੂਰੇਸ਼ਨ 1s2 2s2 2p4 ਹੈ। Let us see what happens when a molecule forms. First, let us see in 1s atomic orbital. As both oxygen atoms are having 2 electrons each in 1s atomic orbital, it shows bonding as well as anti-bonding molecular orbital will have 2 electrons having opposite spin. Now let us see in 2s atomic orbital. As both oxygen atoms are having 2 electrons each in 2s atomic orbital, it shows bonding as well as anti-bonding molecular orbital will have 2 electrons each having opposite spin. Now let us come to 2p atomic orbital. As both oxygen atoms are having 2 unpaired electrons, whereas 1,2p orbital is having 1 paired electron, sigma 2pz bonding molecular orbital, pi 2py bonding molecular orbital and pi 2px bonding molecular orbital are shown here having 2 electrons each, whereas pi star 2py anti-bonding molecular orbital, pi star 2px anti-bonding molecular orbital are having 1 unpaired electron. Bond order is equal to 1 upon 2 into Nb minus Na. It is equal to 1 upon 2 into number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. So, bond order is equal to 1 upon 2 into 10 minus 6. It is equal to 1 upon 2 into 4 or it is equal to 2. It also shows the presence of 2 double bonds in oxygen molecule. For diatomic oxygen molecules, the increasing order of energy of molecular orbitals is sigma 1s has lower energy than sigma star 1s. It has lower energy than sigma 2s. It has lower energy than sigma star 2s. It has lower energy than sigma 2pz. It has lower energy than pi 2px. Its energy is equal to pi 2py. It has lower energy than pi star 2px. Its energy is equal to pi star 2py. It has lower energy than sigma star 2pz. With the help of energy level diagrams, we can conclude that oxygen molecule has two unpaired electrons, so it is paramagnetic in nature. Students, I hope that you all have cleared your doubts related to molecular orbital theory. See you next time. Till then, bye.